Welcome back for another Super Magnet Man video. This one is on a favorite subject. We get a lot of calls about this, emails asking about it, and we've been working on this for many years. We thought it might be a good time to summarize some of what we know about magnetic levitation. So the first thing is, everybody would just love it if you could take two magnets like this and set them on top of each other and they just float. Doesn't work, as we always find out. As soon as you let go, the magnets are going to snap together. We know that if we do something like with our bouncy magnets and we put a rod in the middle, we have restrained the movement. Now we get to take advantage of the bouncing effect that we get from levitation, but it's not what we want. We really want the magnets to be floating without anything. And so then there's another technology. CMR technology makes this special magnetized pattern of magnets that will hover. It actually snaps together and stops right before they would contact each other. The problem is, if I take the rod out of the center, they snap together. Not what we want. So that leads us to the next thing we look at, diamagnetism. Diamagnetism is a magnetic property. It is something inherent to the material, and there are many materials that are diamagnetic. The definition is that it tends to become magnetic or magnetized in a direction that's 180 degrees to the applied field. Okay, now when we look at something that's ferrous, a ferrous item works like this. If something is ferromagnetic, you will see that if a magnetic field here is applied, and let's say it's the north field, and I take a piece of steel and put it here, the field is applied in the same direction as what's applied. So if this is north, it's going to put north over here and south here, and that is what makes them stick together. Well, diamagnetism does it exactly the opposite. It says if you're applying a north pole in this direction, it's going to give you a north pole coming back. So it repels. Now, one of the common experiments in diamagnetism is looking at pyrolytic graphite, and we're going to take a look at that. But in looking at the properties of materials, the pyrolytic carbon, as it's called, has actually the highest diamagnetic property of all. It's about a 40.9 on the scale of the units of measure that measure it. By that same scale, bismuth is a 16.6, and then it drops all the way down to 1.6 for carbon, 1.0 for copper, and water is 0.91. That's diamagnetism and what it does. We're going to start by looking at pyrolytic graphite, and it's a very special type, or pyrolytic carbon. It's a very special way that they make it, and it gives it this tremendous field. The 10 millimeter cubes, these are N40, and the surface Gauss is around 5,000, 5,100 on these. And so we're going to try adding a little bit of weight to it. And what we have is the little bitty squares of a business card material, and it does well. Then we'll add the third one and a fourth one. And you see it's still, by the wobbling, we can tell that it's still floating, but you can tell the gap has compressed quite a bit. Now let's understand what this size of paper is. On this other one, we also have paper floating on top. But I started with one normal business card, and I cut these out, and so that you can only see, you can see just how much I actually used in making the paper that's sitting on both of them. So this is not supporting very much weight, but it does support some. You can add the weight to it. It sinks the field a little bit, and it goes down a little bit, and it goes down a little bit more. Now the second setup is a larger set of magnets. These are half-inch square magnets, or cube magnets, and they're N50, and we have about a 17 millimeter square piece of pyrolytic graphite on top of it. And it is about it's a little less than a millimeter thick. Both of these pieces of pyrolytic carbon are about a millimeter thick. And I've added the paper to it, but I made larger squares of paper. Now, I don't have any scales that can measure this small of a weight. My scales start at 1 gram, and it would take quite a few business cards to get up to 1 gram. Take 4 or 5 of them to get up to 1 gram. So I'm just showing it to you in the size of the paper that I've cut out and put on top of it, and you see how it floats it with up to 5 pieces of paper on top of this one. So these are larger pieces of paper, so it is supporting more weight. So now we've looked at the pyrolytic carbon here. The next one down was bismuth. But bismuth offers us some very interesting options that we don't have with the pyrolytic graphite. The one thing, keep this in mind, with the pyrolytic carbon, the magnets have to be arranged like this: north, south, south, north, okay? And what you end up with is 4 cubes like this, and then your pyro is usually going to float in this region. When you look at this, you can put the pyrolytic graphite on there and it'll float. If you make it a tiny bit too big, it will not stay on top. If you try to put it on one magnet, it will float off in every direction, just like 2 magnets do. This particular arrangement says that the material over this one is giving it a north pole down, trying to make it move, but this one is turning it south and it's trying to make it go back this way. And this one, and so you can stabilize it and it'll sit and float forever, but it's not supporting much weight. Let's see what we can learn from bismuth. And taking a look at bismuth, let's learn just a little bit about bismuth first. Bismuth requires a different orientation than what we saw with the pyrolytic carbon. In this one, we're going to have a magnetic field above where we're looking at. And you take a piece of bismuth here and a piece of bismuth here with a magnet in the middle. Now, where the lifting force comes from is this field that's being applied from this magnet is attracted to this, and it picks it up. But then it reaches a point, if it's balanced correctly and set up right, the magnet will reach a point to where it is approaching the bismuth, but it doesn't have too much force. If this gets too close, then it pins it against the upper bismuth, and the force of diamagnetism is not strong enough to push it away. So what we do is we balance the forces out. We want to get enough magnetic field here so that it's pulling it up and it floats off of the bottom, but we have to have it so it's not so strong that it pins it to the underside of the upper piece of bismuth. And so that takes a little bit of a delicate operation. So let's take a look at what I've made to explore this phenomenon. I've got 2-inch cubes on each side, and then I've got 2 pieces of bismuth in the bottom. I've made an acrylic shield on the bottom so that I can see everything, but it doesn't have any effect on the magnetism. I've got 2 pieces of bismuth. Now, in some of my experimentation I played with, does it make a difference how thick the bismuth is or not? And within a range, it really doesn't make. If I made it half as thick, I don't see any difference in how it operates. And so we're not going to actually look at that, but from experimentation, I did not see that the thickness of the bismuth beyond this point made that much of a difference. And so I got the idea. I said, okay, if it lifts and I'm using this upper magnet, then I should be able to adjust the height of this magnet up and down, which will increase this pull force. And then if I neutralize this distance between the 2 pieces of bismuth and I add weight to my magnet, I should be able to get useful amounts of levitation out of it. And so I did it with just the magnet, and you can see the magnet floats pretty good by itself just in the center. And then I added a 1 gram piece. I calculated with this acrylic plastic roughly what a gram would be. I don't have any scales that can measure in the milligram range, so I just calculated, and I got pretty close to 1 gram for this piece of plastic here. And then we go up to a 2 gram piece based on diameter and subtracting out for the hole for the magnet, 3, 4, and a 5 gram one, which you see floating in the field. Now, it's hard to tell with this because it's so thick, the air gap is so small, and if this is not perfectly in the center, it does tend to tilt just a little bit, and it makes it kind of hard for you to see in the camera, but I show you because you can see it spinning and rotating through, and it works pretty well like that. But what I wanted to do now is just recap the data that we got when I did these experiments. So let's take a look at that. So in taking a look at this data, let me first explain the experimental process a little bit. Well, the first thing that I did is I've got this platform made so that I can adjust the screws. I had to make some plastic tools that would fit on here and allow me to turn these screws just a little bit at a time. And I can move it to get it accurate until I could get the material to where it floats, and then I would use a little straw and blow on the edge of it until it spun and rotated freely. The measurement that we have, distance from the top of the acrylic to the bottom of the 2-inch platform. That's this acrylic, the top of it. Now actually the bismuth is a little bit lower than that, and the center line of the magnet would be lower still. To the bottom of this, you can see that the 2-inch cube sits on this bottom piece of wood, so it would actually be 4 or 5 millimeters farther away from the magnet and another 4 or 5 millimeters away, maybe 6 or 7 on the bottom. But the measurements that I took with the calipers were between here and here. That's this distance. Then the weight without the magnet was the weight of the disc. Now the disc, the little cube magnets themselves actually add to the weight, but they're also contributing to the lifting force, and they're exactly the same in all 5 of the pieces. So I really discount that. I'm just going strictly by the acrylic. I started with just the magnet. Then I went to one that was very small, 0.25 grams is what I calculated that weight to be. Then I made one 1 gram, 2 gram, 3, 4, and 5. Now, the Gauss measurements I made from looking down on the magnet to the left side of the bismuth. I sort of lined the probe up so that it was right over that edge of the bismuth to give me just sort of what the boundaries are on the sides, and then a reading in the middle. And you can see that we go 95, 174, and 99. And I'll explain in a minute why this was important information. And as I increased the weight, I would have to lower the magnet, the cube magnet, to pick up the extra weight and be able to get it closer and closer to match up. At first, I went from 116 millimeters to 106. And then I sort of looked and I said, well, I dropped 10 to go from 1/4 gram to 1 gram. I need to move a little bit more, so I moved about 12 millimeters to pick up double the weight, going from 1 gram to 2, and it got pretty close. By the time I balanced it out, it was 93 millimeters away. Then 83, 77, and 71. You notice in the last steps, it's not moving as much. My percent increase in weight, I'm not continuing to double the weight, I'm just going up a little bit more. The other thing is how the gradient affects this. And that's what I want to take a minute and discuss now on the bismuth and how it's working. When I talk about the gradient, it's how the magnetic field is changing over distance. And when I'm 116 and 106 millimeters away, if you could visualize the magnetic field, it might look like this. So you're not seeing as much variation out to the sides, and if you go to the next layer down, you won't see that big of a drop in flux. That's because of the gradient. However, when this gets closer, I'm now moving into the part where the gradient actually increases. And since the gradient increases, that means the flux between the upper bismuth, the lower bismuth, and the magnet itself, due to that distance, that gradient is different. And so when that happens, I found that I would have to come in and this platform would have to get a little bit closer. And I would change the air gap between the 2 pieces of bismuth, which gets it down. You reach a practical limit that you can't put more weight on this than it can handle because of that gradient change. So if you had a larger magnet and were farther away, you could probably pick up more weight. One of the things that I got to wondering, and that's why I've got this full setup here, is, okay, if this works, how would it work if I got 2 of these to work together? Is it possible to get them to work together? And so that's what I've made, is this setup with 2 magnets, and I've got this so that I have 2 ring magnets where I have taken some of the mass of this away. I wanted to see how that would balance out. And so now we can slide this magnet in between and adjust it and we can get it to where this floats. It's a little bit harder to tell exactly when this is floating because it's got a little bit of a sag, which creates a little bit of a bend over that distance. But this piece weighs 74 grams. So it's a big step up from these that weigh 5 grams, and the two of these magnets did work together well. In summary, to wrap this up, think if we had someone that worked on setting up a set of servos that could position this magnet up and down dynamically, and at the same time monitor these two and adjust this dynamically, we could put a set of magnets in the middle, and within a load range, we could apply a load to it, and it would automatically make these adjustments until it floats again, and it wouldn't need to keep moving it all the time. It would only need to move it initially, and then it would stay. And then if the load changed, it could have dynamically adjust itself up and down and recenter it. Like I said, I'm an electrical engineer, more for power systems, not that much in electronic servos and everything, but conceptually, I think that would give us something that would be dynamic, and it would be able to make it levitate and float using the bismuth configuration. And it may be possible to balance some of that with pyrolytic. We might be able to use the pyrolytic carbon in some way to help balance and give us a little bit more adjustability with it. But right now, I wanted to let you know where we were with levitation and the things that we've been doing and how you may have some ideas to make improvements on this. We look forward to seeing your comments and replying to them on the Super Magnet Man site. And if you need any magnets, you know where to go.